So now we come back to work. Well, work can be positive or it can be negative. So for example, if you have a truck and you have a ramp and you have something that you want to push up, so you apply a force in the upward direction and then it moves upwards, so the displacement is also in the same direction, and therefore cosine theta is cosine of 0, which is 1. And so in this case the work done by this force by F is positive. But suppose in the same situation you were lowering out some cargo, so you wouldn't bring it here and let it just slide down, especially if it has wheels. So what you do is you push upwards with a smaller force and it slides downwards, and you keep pushing it up and it keeps coming down, so that way you make it come down slowly. So the force is upwards but the displacement is downwards. In this case the work done by the force is less than 0, or it's negative. So work can be positive or negative. It's positive when the displacement is in the same direction as the force, and negative when the displacement is in the opposite direction to the force. Now another thing we will see is what happens when the force changes as you go along. So as you're pushing it, you're changing the magnitude of the force. So in this case, if we take an example of, we have a displacement here and that's the force that's being applied, and suppose the force is applied is like this. So it's not a constant force but it's changing, and we want to find the work done in going from A to B. So the work done in going from A to B, and this distance would be our total displacement. So in this case we break this up into a number of small parts, and then we consider the work done by in each of these parts. So let's say we take this one, so from here to here it goes this way. This displacement is delta x, and the value of this force can be taken as the middle of these two, so it can be taken this much. So that will be the force in this portion of the motion. Then the work done, or the delta W, which is the work done in this little part, is going to be the force in this little location times the delta x. And then, well, the W, which is the work done from A to B, would simply be the sum of all the delta W's. So we'll add up the work in the first column and the second and the third and so on until we reach that end, the other point, and that will then be the sum of all the forces. So that's I is 1, 2, 3, 4 and so on. Well, we can write it I equals 1 to n, where I is 1 here and 2, 3, and the last one is n. And well, we can extend that to say that the work A to B in the limit when delta x tends to 0, then this summation of fi delta x become the integral of f dx from A to B. So well, here the force was in the direction of delta x, so we didn't do the cos product or the cosine theta. But if you want to write f as a vector, so f could be in any direction and the delta x could also be in any direction, then the work done would be the integral of f dot, well, instead of dx we write dr, because it could be 2D or 3-dimensional, and this is from the initial position to the final position, whatever that is. Now, if you have the object and you have many forces acting on it, and then there's a displacement, then we can add up the forces, and instead of F, we would then write the F would now be the sum of all the separate forces. So the work can be written as integral of sum of all the forces times dot rather dr, where Fi would be F1, F2, F3, and each of them could be variable. Now we'll do an example of this kind of a force that's variable, and that is a spring mass system. So we'll take a spring and we'll attach a mass to it, and for now we will ignore friction. So we have a horizontal surface that's a rigid support. We have a spring, let's say it comes up to here, and we attach a mass over here, M, and we say that the center of this mass is x equals 0. The original length of the spring does not come into the equation, it's just how much it displaces from the mean position that comes into the equation. So this x equal to 0 is that point where the spring is unstretched or uncompressed. It's the natural equilibrium position of the spring. Now we hold it from here and we pull it to the right. So as we pull it to the right, we apply a force to the right, and it comes up to, let's say, here. So we are applying a force, that's the applied force, and in order to hold it here, the spring is pulling it backwards, which is called the restoring force. So the spring is pulling backwards, we are pulling forwards. Both forces are exactly equal, so this just stays where it is. And here we say, well, that's our value of x, whatever that x is. Now we know that if we want to pull it further, we have to increase this force. So as we increase this force, it will go further, and because it's in equilibrium, this force will also increase. So one thing we see from here is that the restoring force is proportional to the displacement. The more you want to pull, the bigger the force applied, and the bigger the restoring force if you hold it at that point. So we get a relationship that the restoring force is proportional to the displacement. Now if we were to, that's the mean position right here, if we were to squeeze the spring to some position, so we apply a force this way, that's our F applied, and the spring is now squeezed, so the spring is going to be pushing outwards. So the restoring force is now positive, and this is x equal to 0, and this is some negative x. And again, the restoring force is proportional to x. Now, we know that we can have different kinds of springs. Some springs would require just a small force to pull it out, which means the restoring force is small, and some would require a great deal of force to pull them out, so that that spring would be more stiff or harder to pull. So to account for different kinds of springs, or different strengths or stiffnesses, we introduce a term which is written as a K, which is called the spring constant. And that also becomes the constant of proportionality, and so Fs becomes equal to K times x, where K is the spring constant and x is the displacement from the mean position. The original length of the spring, or the total length of the spring, does not come into this equation. Now one more thing, when x is positive, if we take this as the positive x and that's the y, so if x is positive, the restoring force is to the left, and when x is negative, the restoring force is to the right. So to fix that, we need to put a negative sign over here. So the restoring force is the negative of kx. When x is positive, restoring force is negative, and vice versa. Now, we would like to make a little diagram here. So the x equal to 0 is here, just straight under it, and on the right side this is our, let's say, x, and this is, let's say, an equal distance, a negative x. So this is x equal to 0, and that's our plus x, and that's our minus x. On this side we draw the restoring force. So when x is here, the restoring force is to the left and it's negative. So it's, let's say, here. And then as x gets smaller, the magnitude of the restoring force gets smaller, smaller and smaller. At x equal to 0, there is no restoring force. And then at the other end, when x is negative, the restoring force is positive. So this is the positive direction. So it's somewhere here. Well, this turns out to be a straight line. And the reason why it's a straight line is because f is kx. And that's an equation for a straight line. Now, if you want to find the work done in going from any position, let's say from A to any position B, which could be here or here or here, anywhere. So let's say we have A and B here and here, and the spring is going to the right, so it's moving to the right, and we remove this applied force. The spring is now pushing this mass towards the right. As it pushes it, the mass accelerates because F equals ma, so the force creates an acceleration. It keeps getting faster. By the time it reaches here, the force becomes 0. The spring overshoots, keeps going further, and the spring starts pulling it back, slows it down, and it starts going backwards. We want to find the work between these 2 points done by the spring. So we will use the work equation that we had up here. Force equals F dot dr, or in this case F dot dx. So the work going from A to B is going to be the integral of F dx from A to B, and F is minus kx dx, and that becomes 1 by 2 kx squared. Okay, so when you integrate x, when x squared by 2 becomes this with a negative sign, and the limit is from A to B. So this becomes, when you put A minus B, it should become 1 by 2 k. We substitute the B first with a negative, so it's kx A squared minus half kx B squared. So it's from the initial position to the final position, and this is the work done by the spring. Now we can have a look here. So if it's going from A to B, the x is positive, the force is positive, so the work done is positive. So the spring does positive work going this way. If you start from, as the spring is going, and this is your A and this is your B, the x is increasing, but the force is negative. So the work done by the spring is negative in this portion, and we can see that from here. If that's A and that's B, B is bigger than A, so this is going to be negative. And going from A to B over here, A is bigger than B. Both are negative, but when you square them, the negative goes away. So A is bigger than B, so the work is positive. So going this way, the work is positive, then the work is negative. When it's going back, the work is positive, the work is negative. So if you start from here and reach here, the total work becomes 0, and comes back to here, it again becomes 0. Or if you start from any point, goes around and comes back to the same point, well, it still goes back to 0 because the 2 points are the same. Now, one example on this. If we have that's what we would probably do in the lab also. We have a fixed place, we have a spring, and we have a string and a pulley, and we attach some weight over here. So when there's no weight, this is x equal to 0. When the weight is attached, this goes down, comes down here, this is pulled to the right and comes to some value of x. So let's assume that we have 200 grams over here and it moves the distance 5 centimeter. So what is the value of k? So we see from our earlier equation, here f equals minus kx. So we can say F equals minus kx, and F here is the force pulling here, which is the tension, and that will be the same as the tension here. Well, this is good if you allow it to come down slowly and then you stop it over here. It's not an oscillating kind of situation, so you just slowly let it come down. So the force is simply the weight, which is 0.2 kilograms times 9.8 meters per second square. It's minus k times x, and x is 0.05. And so k is 0.2 times 9.8 divided by 0.05, and that comes to 39.2 newtons per meter. Now, even though we have a negative sign here, x is positive and f is positive, but we keep the k as the absolute value. K is always taken as a positive value. So this means that if you applied a force of 39.2 newtons on this spring, it would stretch by 1 meter. Now, what is the work done by the spring? Okay, in this case, the spring is pulling back, but the displacement is positive. So the work done would be negative, and the work done would be given by half k x initial square minus half k x final square, and that would be half of 39.2. X initial we can take as 0, and half 39.2 x final is 0.05 meter, and that comes to minus 0.049 joules. It's negative because the force was pulling to the left, but the displacement was to the right. Now the work done by the weight, by this weight, is positive, 0.049 joules. So this is doing positive work, and this is doing negative work. Or this tension is doing positive work because it's pulling to the right and it's displacing by the same amount. Okay.